So yeah, if you haven't already, make sure to fill out this attendance form. It'll just ask you your name, your email, and your Discord username if you have it. All right, I think we will get started now. Um, so welcome. My name is Zach, and I'm gonna do this workshop, I guess, for quantum circuit practice problems. So yeah, I guess I should talk about that a little bit. So this quantum crash course like series, um, it won't always be quantum circuit practice problems. We're not exactly sure what it will be throughout the semester, but we're still kind of planning it. Um, so it'll just be various maybe lectures or um, just interesting things related to quantum. Martin suggested that we could just look up some interesting quantum term and then research it a little bit and present it. So that's just some of the ideas we had. So it'll be a little bit different every time, probably. Uh, okay, no. So this is just the outline, not much to it, but uh, we're basically just going to do some quantum circuit practice problems, and this will involve the following concepts. And if you don't know what any of these are, that's totally okay. We're gonna go through them together before we get into the practice problems, and we will also have you working in groups. We'll try to split up the expertise as much as we can, so that we can have groups that at least someone knows a little bit what they're doing. So yeah. So the goal is to understand how to use the bra-ket notation and the block sphere to solve quantum circuits. They aren't that large, but yeah. Any questions? We good? Okay. Okay. So there's a lot to cover on this slide. And I think, so I guess, yeah, let me just start by asking. So we have bra-ket notation and the vector representation that we can use with that. Um, can anyone tell me what the vector looks like for the zero het? That anyone that knows it? Martin? You don't know it? All right. You know?
It's like a bar and then zero.
Yeah. Right. But I guess how does it look in like linear algebra
It's
as a
one
vector?
zero.
1, 0, right. I'll write this down. And then for anybody for the one, what does that look like in vector notation? He said 1, 0 for,
Zero.
okay. Yeah. So 0 is 1, 0 and 1 is 0, 1 in vector notation. So let me just write that down real quick. All right. So we said that 0 is represented as a vector, 1, 0, and 1 is 0, 1. And so these are known as kets. And then I'm not sure what word to use here, but the other way around is a bra. So together they make a bra-ket, which I'll show in a second. So this, I guess that's wrong. So then these are just the like transpose of each other in simple terms, I guess. Um, the details here aren't too important because you don't need to use this vector notation today. Um, so 0, 0, or so let's just write the general form, I guess. Or maybe I don't need to write it. Hang on. Okay, does everyone have this stuff down or you remember it? All right, I'll go back to the slides. Let's see. Ooh, I hope that was recorded by this. Well, maybe not, but I'll post the notes later anyways. So, all right. So yeah, and now I guess any questions so far about that? Good. Uh Hello, welcome. So then here are the like general forms of this bra-ket notation. So you can have any quantum state psi on the top. So this is the ket and this is the bra. Actually, let me use the, I think there's like can I use a laser pointer? Maybe not. Anyways, I guess I'll just point at it. So the top one is the ket, and that's what we'll concern ourselves with today. Um, we're not going to really worry about the bra version today. Um, yeah, so you can have any combination of the 0 and the 1 um, with different coefficients. And that's what the A and B are. They can be any arbitrary coefficients, and that's all I'll get into with that so far. Or maybe, hmm, yeah, I guess. Can anyone tell me what like the constraint is on those A and B coefficients?
B squared.
Right, yeah. So let's flip over. Okay. A squared plus B squared has to equal 1. Yeah. Right, yeah. So A and B are actually like complex numbers. So A is equal to um x plus I y. That might be confusing, but um it's just it's good to know, but if you don't know too much about it, don't worry too much about it. Yeah, so um what we're doing here is we're taking the magnitude of the complex number and then squaring it, and same here. So yeah, I will move on to next. Um, so that's just good to know, like as we do our practice problems in a little bit, that you can kind of check your work, I guess, by making sure at the end this is still true. The a squared plus b squared is equal to 1. Just to make sure you didn't throw in another coefficient and mess things up. So that's that. I don't know if we have to go a lot into everything here. Um, we'll cover this tensor product, but I don't think we'll do the inner and outer products right now. Um, any questions so far?
The reason why do you is the reason why you have why the square is equal to 1 because you're normalizing it.
I think so, yeah.
I mean, so how would you normalize that? I mean, I
Um,
forgot that's.
okay, yeah, yeah, sure thing. So let's say we have a vector, v, and it is, um, how should I do this? Um, 1, 2, 3, maybe. So if I want to normalize this vector, whoops, that's like lopsided, but don't worry about it. If I want to normalize this vector, I think you just take the magnitude and divide by it. So you take the magnitude, you get 1 squared plus 2 squared plus 3 squared um, equals something. I don't want to think about it. Um, so then your normalized vector would be like a v hat, I think. And then you just do v divided by
So
v.
it's just a unit vector.
Yeah.
So does normalize just mean you're comparing it to vector?
Yeah, I guess so. So as you can see, these two kets are already normalized because you only have one. Okay, great question. Any others before I go on to this tensor product, and I'll get to the Pauli matrices as well. Good. All right. So tensor product will be important here because um, as you'll see in just a second, let me show this. As you'll see in a second, if you have a quantum circuit, it looks something like this. And you have like qubit 1 and qubit 2. Um, and then yeah. So then each like line can be is representing a qubit, and it'll have like some gates on it. I don't know. Doesn't really matter right now. Um, so you can represent the quantum state of both of these qubits together by, we're just going to call it psi, just because we want to choose a variable. And then we can actually combine the two qubit states. Does anybody know how this ties into like the uh, tensor product? Anybody? Yeah.
Is each operator is like a transformation of the vectors, so you can just like stack them.
I'm not sure about transformation, but I think you have the right idea. You said you can like stack them, right? So what you can do is I want to represent, okay, let's just say like qubit 1 starts out as 0 and qubit 2 starts out as 1. And we're just going to consider the state at this point. Let me, so this is where psi is. Um, so then we can basically stack them. So we can do 0, tensor product, 1. Does this make sense so far? At least a little bit. And then what people do for shorthand notation is they just smush them together like this. And you can do the same kind of thing. Like if you wanted to show the bra of this, then it's I think it's just the same. You're just flipping um, the direction of the notation. Correct me if I'm wrong. Okay. Um, all right. So that is, I think that's kind of the extent of the tensor product knowledge here that we need to know for today. Good with everyone? All right. Pauli matrices. Um, so I guess, can anyone tell me, uh, how should we talk about this? Can anyone tell me what the Pauli matrices, like, I don't know, anything about like what's their relevance with quantum circuits, I guess.
They kind of act like gates, where they change the state of a, like it's like a function where you put in a vector and then it does it does a function on it and then it outputs another vector that it's different from its original state or in a noticeable way.
Right, exactly. So if you take this quantum state, for example, this, let's write it again down here, psi equals 0, 1, then you can use, let's say like we can make psi 1, uh, hang on, psi 1, um, we can act the sigma x gate, or would we have to do a tensor product? Yeah, because we need it to be higher dimensions. All right, that's a little too much maybe, but actually it's not. Hello, welcome.
Okay, so this is a quantum computing club, right?
Yes.
Oh,
So, any questions? I mean, this might not make a lot of sense. So let me let's get another example. So let's say we have, let's just say phi, just another variable, and it equals 1. And then I want to apply one of these Pauli matrices on it. Um, so let's just do the X matrix. And that, does anyone know what that becomes if we apply this? Anyone else, maybe? then becomes 0, right? And I think that'll make a bit more sense in a second when we show the block sphere. Any questions? Yeah. Yes, so that's a great point. So this is, I guess I'm just showing you like this is all bra-ket notation. Um, and you can convert each and every one of these to linear algebra if you're more comfortable with that. I certainly was when I learned this, so I like to do that sometimes, but it can be done either way. And same with these, we saw that these are like matrices. I don't remember what's in them.
So 0, 1, 0, 1, 0.
0, 1, 1, 0.
Yeah.
Okay. Um, yeah. So let me just yeah, any questions before we go on? I'll show the block sphere and um great question. I'm not sure. Yeah. Yeah, because I guess tensors are like higher dimensional like vectors, so yeah, that's just a mathematical term. Um, Great question though. Kronecker product. Okay, sounds right. All right. Well, I don't want to dwell too much on this, so let's just move on for now. So we'll go over this, and then I think it will be time for the practice problems. So this is just a list of, I guess, the most common quantum gates, quantum circuit gates. You have a quantum circuit, and you want to apply gates on your qubits. This is how you can do it. So we have the three Pauli matrices at the top, X, Y, and Z. And what you can, so yeah, we have those three. We have Hadamard, and then don't worry about phase and T. Um, Controlled knot. Don't worry about controlled Z. We have swap, and we have Toffoli. So those are all, what I just listed are what will be in the practice problems. So let's start with X, Y, and Z. Can anyone uh, tell us like what, before I get to that actually. So here's the block sphere, and this is not in our Cartesian space, X, Y, and Z. Well, there is X, Y, and Z on there, but this is called Hilbert space, which is like a different mathematical like space. Um, that's not too important, but it's just good to know. So you have the one state on the bottom, and you have the 0 state on the top. And this is just your origin, and this is where like your vector starts. So basically, when you have a quantum, when you have just one qubit, um, if it's in state 1, you have a vector pointing from here down to the 1. If it's in state 0, you have a vector pointing from the origin to 0. And then you can also do some fancier things with some of these gates that get it into like superposition states that the vector is pointing along the equator. So that's just to give you an idea. So we have X, Y, and Z coordinates here. Can anyone tell us like what's the logic behind these Pauli matrices X, Y, and Z in terms of the block sphere? Does the question make sense?
Almost like there's like one of you guys, for example, up here goes, whoa.
So which one? Like what do you like in which axis, I guess?
Oh,
Does that make sense?
something does the Z axis, right? No.
Yes, kind of. So the axis in the name, what about it? Right, exactly. So if we had a qubit at state 0 straight up, and we applied the X gate, the Pauli X gate to it, that means that we are like sticking that vector like along this axis, and then we let it just like swing around 180 degrees till it's down here. That's how that works. So you can look at it like it's a rotation about that axis. Does that make sense? So then Y and Z are the same idea. So if you had a qubit that was in either state 0 or state 1, say, let's just say it's in state 1, and you applied a Pauli Z matrix or gate to it, what would happen?
Where did it start?
It's in the 1 state. Purely 1. So what we just said was, yeah, so it's the Z gate, and we're applying it on the 1 state. It doesn't do anything, right? Because it's rotating about the Z axis, which it's already on. So just nothing happens. So that's good to know for the practice problems we have coming up. Okay. Hadamard is a good one to know. Can anyone tell us what that does in relation to the block sphere? We'll wait for someone. Do you know? You don't know? Okay. Okay. Ben? Or yeah, go ahead. It entangles superposition. Right. Not entanglement. Entanglement's different. So yes, if you have a qubit in the 0 state or the 1 state, so let's just say 0 state, and you apply Hadamard to it, it just takes it to the equator, basically. So then you have a superposition of 0 and 1. You have equal parts, 0 and 1. So you have an equal probability of being in the 0 or 1 state when you measure, which that's not too important today, but okay. Any questions so far on the Pauli matrices and the Hadamard matrix or gates?
I feel like I'm a vague memory, but I feel like you use the Hadamard gate to like find the spin of the QM. But is that wrong? Does it perform a Hadamard gate and then that's to like reset it and then like you perform like one of the Pauli X1 or Z gates and that gives you like a certain value. And by performing the Hadamard gate before one of the Pauli matrices, you get like a certain piece of information that we wouldn't have found. We just didn't.
Possibly. I would think maybe like phase. You get phase information from that, but I'm not 100% certain. That's a good question. I'm not certain. Yeah.
I think you mentioned like probability, right? There's something here. Like, what is there? Okay, what's the relationship between this and like maybe entropy or something?
Entropy? Mm, I don't think so.
Probability or entropy?
Well, I guess one thing is like with the probability,
They
like
are.
that's why a squared plus b squared have to equal 1 is the probability of being 1. Way. It's really a probability.
Yeah, that's a great question. We should talk later. Because I don't know. Yeah. Okay, so we've got 4 gates so far. And okay, so Hadamard, if you apply it to the 0 state, you go to the equator. If you apply the Hadamard to the 1 state, you also go to the equator. But I don't remember which is which, but like one of them, if you start at 1 and apply the Hadamard, you'll go to like, I don't know, like this side of the equator. But then if you apply it to the 0, you go to like this side. So you still have the same superposition, but it's like a different phase. But that might be too much right now. So and then if you apply a Hadamard gate twice, if you apply Hadamard on the one, you get to the superposition, the equator. If you apply it again straight away, you go back to one. So if you apply Hadamard twice, you just end up right where you were if you were in 0 or 1. Okay, so I can maybe write that out a little bit. So Hadamard on 0 equals, and this is where we kind of get into that idea of a squared plus b squared equals 1. So we have 0 plus 1. And then if you do Hadamard on 1, you get 1 over root 2. Oops. 0, minus 1. And then if I were to apply a Hadamard on, well, I don't want to write that out, but let's start with this. So for this guy, we can check to make sure that the a squared plus b squared is still equal to 1. So you can just distribute this to here and to here, and you'll get that a equals 1 over square root 2, and b also equals 1 over square root 2. So then a squared plus b squared equals 1. 1/2 plus 1/2 equals 1. Does that make sense so far? Is that good?
Right, so why would be the sum of those two for 0?
For the 0? So this kind of, you mean like as opposed to like the minus here? Or
Like, why aren't we multiplying it with like doing the tensor product?
okay. Oh, you're saying right here?
Yeah.
Okay. Good question. So basically, you can think about it in linear algebra terms in this case, or you can think about it in bra-ket. So let's think about it in bra-ket notation. H is a gate, and 0 is a state. So gates act on states, meaning they just multiply. So in linear algebra, we can say that H is a matrix and 0 is a vector. The tensor product, I believe, is only like relevant for when you have like multiple qubits and you're trying to combine them. So like I showed up here. Does that make sense? But in this case, you have, so let's show it here, I guess. So for this Hadamard gate, what we can do is we have psi equals 0, 1. And then the next psi after that Hadamard gate would be equal to, anybody know? Like how to write, like how would I write the Hadamard gate with this notation? Sorry, that doesn't make a lot of sense. I'll just write it. Right?
You're performing the gate on 2 qubits in the same.
No. I'm performing only on the 0.
Oh, okay. Then you're finding the compounds.
Right. So does that make some sense? Any questions? I think sometimes you have to struggle a little bit to understand it better. So maybe I will just get into the practice problems and we'll come around and help, and we'll try to split up the teams evenly. Let me just see if I can finish up this note. So, okay. So that's psi one. So let's say this is psi one, and then this is psi two. So now psi two would look like this. We're just not evaluating this because I don't feel like writing it all out. And then what would be in front of this one state? X, right? And the X is just the poly X gate that we saw. Okay. All right, I'll briefly discuss this controlled knot. So, and then I'll just let you guys maybe figure it out after that. So, controlled knot, or can anyone else describe it maybe? Yeah, Ben?
So I think the one of them is like, if this one's on, then that one also turns on. If that one's off, and that one
Right.
turns off.
So there's a control and there's a target. So you can see this is a gate that spans 2 qubits. It's on 2 lines. All these up here were just 1 qubit, 1 line. But in this case, you have the control is the black dot, and then the target is this like circle with like a cross. So you can always remember that because the target is like, it looks like a target kind of like you have like a cross on it, and or it's like yeah, something like that. So basically, if this top qubit has a 1, then you're going to flip the bottom qubit. You're gonna use an X gate on it, which is basically like a NOT gate. If the control qubit is 0, then you do nothing. Yeah.
So would each row indicate like an absolute state? And like in the first two like columns, you see that it didn't change anything, but on the last two columns, you see that it like flipped.
You're talking about this, the matrix?
Yeah.
Um, yeah, I think you're probably thinking along the right track there. Like, um, I don't know. It's hard to think about 4x4 matrices in ways that make sense, I think.
Because when I was looking through Qiskit, they said they treated these as like linear transformations. So like you're applying a transformation on a vector, and then see each column corresponds to like for the first column is like, I mean, for like if you look at the poly X, like the first column represents like the 1, like 0 state, and then the second column represents the 1 state. So by performing the X gate on the 0 vector, we get the 1 vector. That's what I was thinking. So when I was looking at the NOT gate, I was like thinking, okay, so on the 3rd and 4th state, it just flips it, but it doesn't do anything to the first 2. So is there like and my second question is there like another one where it does it for the first 2, but not the second one, or is it?
Yes, and that would just be flipping this, right? You swap the target and control, then you get that.
So
That
how
makes
would you write
sense?
that as like just like,
You would do exactly what you said.
oh,
I think you would just take these 2 columns, put them here, and take these 2 columns, put them there. Yeah, great question. That's a good way to think about it. I didn't think about it like that before. All right. Does that like make sense? The intuition there, the controlled knot. One of them's control, one of them's a target. Okay.
The block.
What? Sorry.
Due to the block sphere.
So the block sphere gets weird in higher dimensions. So the block sphere represents here just 1 qubit. But then when you have 2 qubits, you have higher dimensions of like states. And it gets weird. So don't worry about that, maybe. You have to just kind of think about it 1 qubit at a time with the block sphere. That's how I do it. Yeah.
you're gonna get into phase.
We won't get too much into phase today, I don't think. So let's just take a look at the practice problems. Wait, whoops. Okay. Well, I wrote this. Let's not right now. Okay. These are the 3 practice problems. So I just wanted to discuss a few things before I let you work on it on your own. So here is NOT gate or poly X gate, X gate. These are all synonyms. So, and then next to it is this Z, which represents the poly Z gate. And then we have the H, which is the Hadamard gate. Then over here on the right, number 3, we have the Y, which is the poly Y gate. And then in number 2, we have a lot of these C naught gates, which, as you can see, is the same thing as this NOT gate, but it just has a control tied to it. And as a reminder, that's the control here and the target at the bottom. And then over here on the right is a different variation of this kind of same thing, except now you have 2 controls. So you need to have a 1 on both of these qubits for this action to be taken. So if you have 0, 0, nothing happens. If you have 1, 0, nothing happens. You have 0, 1, nothing happens. It's almost like an AND gate paired with a controlled NOT. I don't know if that helps. For anyone that knows digital logic, that might help a little bit. But that is it. And every qubit starts with the state 0. That is important. Every qubit starts with the state 0. So now I will let you pause the video so that you can work these quantum circuit solutions out yourself. All right, moving on. So now the next part that we didn't get to in the in-person session today, but you could, if you are following along at home, you could try this. So with this final quantum state that you've derived an expression for each circuit here, you can take that state and sketch the probability distribution of it. So here are 2 examples. One, we're applying a Hadamard onto just the 0 state. Remember, these are all by default starting out as the state 0. So we apply the Hadamard to it, and then we measure, which means we're just putting it into a superposition state and then measuring it. So as we expect, we see a perfect 50-50 outcome. And then similarly, this is just the exact same thing, but on 2 qubits instead of just 1. And now we have higher dimensions now. So we have 4 possible states, combined states of the qubits. And this notation is just saying this little dial is kind of just saying that you're measuring it. And it means you're collapsing your quantum state into classical measurement, which means that it can no longer be in a superposition. We can touch more on this in future sessions for these crash courses. But for now, just understand that it means measurement. And the Z is indicating that you're measuring it along the Z axis, which is the computational axis, because that's where your 0 and 1 are on the block sphere. Yep. And then this arrow going down to this C4 line is just indicating that this C4 line is a classical line. You don't need a qubit. You don't need quantum information anymore once you've measured it. And again, we'll probably go into this more in depth later on. And finally, here is the solutions to the practice problems. These are just the final states, but and excuse my maybe bad handwriting, but the number that's enumerating each of these is just indicating. So okay, here is size 0, and then after the first first column of gates, we have psi 1, psi 2, psi 3, psi 4, and then the same idea over here and here. Hope that makes sense. I don't have the solutions for the probability distribution, but you should feel free to go to the IBM Quantum Circuit Composer website. If you just look that up, IBM Quantum Composer, you should be able to find it. You can make an account for free, and you can go in and play with all the gates and circuits. And that's actually how I made each of these circuits, and it'll tell you everything about it. So thanks for watching.